It's my pleasure to introduce Dr. Chen Li from UCI, and I'm going to do a really short introduction to leave more time for the talk. Dr. Chen Li is a professor in the Department of Computer Science at UCI. His research interests are in the fields of data management, data science, AI, machine learning, databases, data-intensive computing, search, and visualization. He was a co-founder and CTO of a startup and an ACM distinguished member, an IEEE fellow, and received an NSF Career Award. And he preferred to ask questions during the talk. So if you have a question, please drop it in the chat and he will answer that. With that, please take away.
Thank you, Zhuo Yu. Let me share my desktop. Let me do it. You see my desktop, do you?
Yes.
With my deck.
Yes.
Okay, good. You still see it. All right. Thanks for the introduction. Thanks for having me here. For this presentation, I also invited some of my team members. They're also on this Zoom session. For the people who are going to watch this video later, please feel free to contact us after you watch it, and if you have any questions. And as Zhuo Yu said, we have 1 hour, but feel free to interrupt my talk if you have any questions. If needed, I can always skip some of the slides later. I think having this kind of interaction is more fun during this talk. So in this webinar, I want to give an overview of a system called Texera. Our team has been building for last now 9 years. The position of this project is an open source system for a cloud-based collaborative data science and AI ML using workflows. I know we have some colleagues at ISI who are also working on workflow systems. Whenever you have questions about workflow system in general, I would be very happy to answer them and talk about some of the differences. So the outline of the talk, I will start with example motivation, a real example to motivate this need of collaborative data science, and that's also motivates our Texera system. And then I will invite some of our team members to show a live demo, which hopefully can make the talk more entertaining, more fun. And after that, I'm going to talk about some of the components, design decisions we have made, including the backend engine, how to make the whole thing suitable for a cloud environment, and how to improve user experiences using the latest AI techniques. At the end, I will conclude by talking about the impact the project has made in our vision. So let me start with the real project. It's called the mouse brain image analysis. I assume people don't have the background of this field of medical analysis. So the domain is in one of our faculty in the medical school at the UC Irvine. Their lab is analyzing the brains of mice. You do not need to go through the detail of this pipeline. The main idea is they have some a mouse, and they took the brain of the mouse and let the brain go through multiple steps, slicing, and then scanning, and then image analysis, how to combine different tiles into one different complete image, and how to combine different images or sections into a big 3D model, and then do the visualization of this brain using open source software. So this is the whole pipeline, and it's okay if you don't know the details. But what's the point? In this project, the main lead is Professor Xiangming Xu. He's a scientist in neuroscience, and his team is doing all the lab work, the slicing, scanning, And then later, as you can imagine, in the whole pipeline, a lot of effort has to be put into image analysis. Their team does not have this expertise. They are good at the bio lab work, but they're not expert in computer science. For this reason, they have been collaborating with another professor, Gopi, Meenakshi Sundaram, from our department. His expertise or his lab's expertise is in computer images, computer vision. So the way they work together is Dr. Xu's team provides the data to Dr. Gopi's team. Gopi's team will write some Python code to do all the things, the stitching, 3D modeling, and then visualization. And then the results will be sent back to Dr. Xu's team. And this is the way they collaborate. But in this collaboration model, they face a few challenges. A main challenge here is this gap of their different backgrounds. Dr. Xu's team, they are biologists, they're medical researchers, but they don't know programming. They don't know Python. The Gopi's team is more on the sales side. They are Python programmers. They know all the Linux commands, how to set up software, how to set up systems, but they have a gap. So as a consequence, the way they collaborate is the Gopi's team will just prepare some Python code, and then let Xu's team run that command, like the program in a single line command. But you can imagine it's not very efficient, mainly because Dr. Xu's team, his technician feels scared by typing some like command in a Linux environment. So this is a gap where they are facing. So the way if you look at the big picture, here is example of collaborative data science. But if you look at the other available solutions for collaborations, we know a few. GitHub might be the most common one for programs. And then we also have Google Docs over Leave. So if you pick a GitHub as example, you may think, why can't we just use GitHub to solve the problem? The issue is GitHub is not designed for uh, this kind of scenarios because it's mainly designed for managing the source code projects. And that does not overcome the limitation of Dr. Xu's team because they don't know programming. And they want something that's more friendly through like a web browser or some GUI interface. And plus, if you use a GitHub, the GitHub only manages source code. The GitHub does not have the runtime environment. For you to repeat some experiment, you have to follow some README file, and hopefully the README file is well written. And then you set up the environment, set up all the libraries, and we know the experience, which is not pleasant. That's why this is not a good solution for this particular case. So I use example to motivate this our Texera system. So in this particular use case, what we have done is we got invited to join the collaboration, and we have turned the Python programs written by Gopi's team into a workflow. This is a Texera workflow interface, and we don't need to go through detail because shortly my team is going to show a live demo. The user experience will be the following. Dr. Gopi's team, they will convert the Python code into a workflow, and Xu's team, they just open their browser, and the browser will connect to this web server, and the browser shows this workflow and multiple workflows, and the technician of Dr. Xu's team will just purely rely on this workflow to conduct the exact same analysis that was done using a Python program. So the experience is very similar to the way we use like a Google Docs or Overleaf or Google Slides to collaborate on a single project, and different people can contribute different pieces of the whole project. And as this screenshot shows, this platform also has many other advanced features like real-time feedback, sharing, and version control. Those are features that are very critical in scientific collaborations. So this is one interface of the website of the Texera workflow. So next, to make it more real, I will invite some of my team members, Chris and Jiadong, to join this to share their screen and do the live demo. So I'll stop sharing for now. So Chris, you want to take over?
Yeah, I'll share my screen. Okay. Yeah. So a brief self-introduction. My name is Chris, and I'm a second-year PhD student working in the Texera team. So for the talk, I'll do a live demo of the Texera platform, and the demo will take roughly 10 minutes. Yeah. So and if you have any questions, then please send a message in the chat. Um, so the website I'm currently showing is one of our deployment. It's a hub website. The link is hub.texera.io. It's public publicly available to the users. So if you're interested, you can come to our website and send a request to us so that we can let you in and use all the interesting features in Texera. So I'm going to log into this website using a Google login. And now this is the interface I can see. So on the left side, there are two tabs. First tab is called Hub, and the second tab is called Your Work. For Hub, I'll explain it later. So for Your Work, it's basically users um, what user can create. So basically, there are three different tabs here. The first tab is workflow. Uh, it allows users to create their workflow and have a list of workflow they created. And the second tab is a dataset tab. So user can upload their dataset and have their list of dataset so that the workflow can use these data set to do a data analysis. And the third tab is a quota, basically showing the statistics of your work. So for example, like how many data sets are unloaded and how many workflows are created. So for the demo, I'm going to show you a brief, like a simple workflow and a simple data set to do a data analysis. So let's first look at the data set I'm going to use. So if I go to this data set, it's a single CSV file. It's an iris data set. It's a widely used data set in machine learning. It has 6 different columns. The first column is an ID of each iris sample, and the second and third column is sepals length and width in centimeters, and the fourth and fifth column is a petals length and width in centimeters, and the final column is this specifies the species of each iris sample. There are total like 3 different species in this data set. So next, yeah, I'm going to use this data set to do a data analysis using the workflow. So yeah, I'm going to use the pre-built workflow I created for the demo. So if I click this workflow, I see a very simple workflow that has 4 different operators. So the interface is a directed graph interface. So you see there's an arrow between the operators. So basically the data flows from this operator to next, and then this operator to the next, and so on. So I'll explain what each operator means. So the first operator is reading the CSV file from the dataset that I just showed. And the second operator is receiving the tuple from the CSV file. And what it's doing, it's written in Python language. So if I look at the code, I basically write the code in Python. What it's doing is it's processing each tuple, and it's multiplying the petal length and petal width to create a petal area, and it's multiplying sepal length and sepal width to uh, yeah, measure the sepal area. And it's then producing a tuple that contains sepal area and the petal area. And the third operator is a RUDF operator, so it's written in R. Um, so if I look at the code, what it's doing is it's getting all the numerical columns, and it's scaling the numerical column uh, to the value between 0 and 1. And it's returning the table. And finally, the last operator is visualizing the data into a scatter plot. So the X column, I specified it as sepal area, and the Y column I specified as petal area, and the dot is colored corresponding to the species of the iris sample. So now I'm going to run this workflow. So the first step is to first create a computing unit. Um, if I click this blue button here, I can create a computing unit. So computing unit is a is basically a computational resource for each user to run this workflow. So user can configure like how many memory and how many numbers of cores they want to use to run this workflow. Uh, I can like select the configuration based on this drop-down menu. So I'll maybe just select 8 gigabytes of memory and 4 cores. And also I can specify the JVM memory size. I'll just make it 4 gigabytes. And if I click create, the computing unit will be created. And once it's created, then I can, this run button will be activated and I can execute this workflow. Yeah, it's gonna take a few seconds. Yeah, so yeah, we can wait. Yeah, so for the good thing about our Texera platform is we provide multi-language support. So within a single workflow, we support both Python and R. We also have like a Java UDF operator, so user can also write their code in Java and as an operator and insert into this workflow. Yeah. So now the run button is ready. So I'll click this run button. It will start running. Okay, so now it's start running. And a good feature in our Texera platform is we support pause of this execution. So there's a pause button here. So I'll click pause. Now the whole execution is paused. Now I can see like the colors and numbers here. So the green color means this workflow has finished the execution. And the purple color means it's currently being paused. And the number here represents the number of tuples that it received and produced. So here, 150 means this operator produced 150 tuples to the next operator. And here there are two numbers. The first number represents the number of input tuples. The second number represents the number of output tuples. Yeah, so after I pause it, I can resume this execution by clicking this resume button. So if I click it, yeah, it's gonna continue the execution. Okay, now, yeah, uh, everything is completed. And I can see the result by clicking this result panel menu and also click the last operator to see the scatter plot. So yeah, I can see this nice scatter plot with the x-axis being sepal area, y-axis being petal area, and the color represents the species of each iris sample. So now what I'm going to do is I'm going to share this workflow to one of my colleagues, Jiadong, so that he can like edit this workflow. So I'm going to click this share button and I'm going to share this workflow to Jiadong. I'm going to give him a write access level. I click share. Now Jiadong can join this session and edit the workflow. So yeah, Jiadong, can you join the session?
Yes. Okay, so I will open the workflow you share with me. I'm on your workflow right now.
So yeah, I can on my screen I can see Jiadong's cursor and what he's doing. So yeah, I'll shadow him and see what he's doing right now.
Yeah, sure. Yeah. So thank you for sharing me with this workflow. So let me just check your code. Okay, and well, I'm not a guy who like to write comments, so I delete all the comments. And the R code looks good. It's short. And now I'm wondering how can I maybe do a little exploratory analysis on this data? And now, how about let me count how many uh, species each species have how many samples there are there. So I'm going to find a aggregate operator here. I'm going to connect with the source operator to count how many samples are there for each species. I will do a aggregation by doing a count on the ID, and the result is going to be number of samples. And I'm going to group by them by the species. Okay, so we'll name it number of samples per species.
Okay.
I've finished my changes. Chris, you can go ahead and run it.
Okay, I can, yeah, based on his change, I can run the workflow again. Yeah. Now I can see this the result of this operator by clicking the result panel. Now, yeah, I can see that there are like 50 samples for each species of the iris sample. Yeah.
Yeah, thanks, Chris.
Okay. Yeah, this is the feature of shared editing that we provide, so users can collaborate using on the same workflow to like edit together and yeah, run the workflow. Yeah. Okay. Thank you, Jadon. You can now leave the session. Okay. Now I'm going to briefly introduce one of the advanced features in our platform, which is a version control. So Jiadong just added this operator, but if I want to remove, like go back to the previous version, we have this version control feature. So on this left panel, there is a versions tab, and I can see all the versions uh, of this workflow. So if I want to go back to the previous version, then I can select one of the previous versions here. Like for example, let's go back to 41. No, not this one. Maybe 40, 40. Oh, 39. Oh, it's not. Oh, it's not.
Could be even earlier versions.
Maybe I'll just refresh it.
Hmm.
Maybe earlier version. Oh.
Maybe this one didn't change.
Not sure. I think it's
Okay.
yeah. I think it's there's some issue on
Hmm.
this yeah version control right now. Yeah, I think it's yeah thing I think we need to take a look. Anyway, yeah. Um, yeah, we anyway we support the version control of this workflow. The next thing I'm going to do is yeah I'm going to yeah maybe share this as a public workflow. So I can make it public, and if I make it public, then I can maybe just log out. And if I go to this hub tab, the hub tab means it's publicly available to the users who are in who has an account on this platform, or even the users who doesn't have an account on this website. So if I go, I'm currently logged out, and if I go to the workflows tab, I can still see all the publicly available workflows here, including the workflow I just publicized. So if I click this button here, I can see the workflow that we just created. And also there are publicly available datasets here. So there are also a lot of datasets that are publicly available. So and also let me just show you one of the publicly available workflows here. These like 3 workflows are the capstone workflow created in the DS4All project. So it's we hold this program for every like summer for high school students to use our platform and build their workflow to do the data analysis. So one like workflow I can show you, this workflow is created by high school students. And it's very like a complicated workflow that's doing a machine learning using a data set from the Kaggle. Yeah. And one good thing is I can log in and I can use this workflow as a user. So if I clone this workflow, yeah, I can clone this workflow and then edit the workflow here, or like even execute the workflow from the publicly available workflow. Yeah. Yeah, I think that's all for the demo that I prepared.
Yeah, Chris, you can keep sharing your screen. Now, before we switch to my screen, any questions from the audience?
I have a question, but you may address it later. So here, this is with my face now. Yeah. So what is the support to basically combine the different components of the workflow? I mean, are you supposed to just kind of go into the code to make sure that the kind of the output of one node is kind of compatible to the input of the node? That's kind of as a data integration person, I mean, I know you've thought about this, but I understand what's the big picture here. Are you supposed to just let people kind of modify the code so that they ensure the compatibility and you kind of put that burden on the users, or is there any support on the tool or plan support? And if it's not already, you can just tell me later.
Yeah, Chris, you want to answer the question? Jiadong.
Sure. I can give I can answer this. So we built this platform to basically let user to collaborate on the same data analysis. And during this workflow construction phase, people usually specify their workflow as few stages, like read the data, clean the data, do some visualization, train a model, and get the result. That's what people's workflow usually look like. And during this process, multiple people are editing at the same time. And during their editing, for the input and output of each operator, we do the schema propagation, which is each data has certain schema, say what columns they have and what's the type of each columns. During this process, we automatically propagate the schema to let user to edit this workflow easily. They don't need to check the data and switch the workflow back and forth. There are some intelligent helper for them during the editing phase. And during the execution phase, they just create a computing unit and click the run button to execute the workflow. So
Yeah. In addition to what Jadon said, the it's all more about kind of the data modeling. For us, the each operator, the input of data of the operator is a table. The output is also a table. We provide two kinds of operators. One's a native operators, like a simple one, relational operator like selection, prediction, join. Those operators, they just provide the data as a table. But when a user writes their own user-defined function, UDF operators, we give some library, and they use our library to make sure the data they produce is also a table or a stream of tuples. So then we can solve this. So that's why it becomes agnostic to the program language. Because if you use different languages, Java, Python, R, as long as you can produce your data as a table, the downstream doesn't care how it's generated. I hope that answers your question.
Yeah, so so I think you answered. So essentially, all the inputs and the outputs are relations, and then you're
Yes.
exposing the schemas, and then the user is kind of understanding what the meaning of those columns are, and then kind of process them accordingly. And
Correct.
yeah, okay. I'll let you please
Okay.
continue and
So we
have
we
about
continue.
later. Thank
Okay.
you.
Any other questions before I switch to my screen? Okay, then Chris, you can stop sharing. I can share my screen. Thank you, Chris and Jadon. So we saw a demo. For the remaining time of the talk, I want to give you a kind of a quick overview of all the challenges, the design decisions challenges we're facing and our solutions. Let's first talk about the backend. The for us to enable this kind of user experiences, we look at what is available on the market, and we realize none of the systems on the market can meet our needs. For example, to mention a few needs, we want to support this and the kind of a interaction between the user and the system during the execution workflow, in particular the pause feature. And we believe when you do data science, especially when you're dealing with a very large amount of data, the execution can take a long time. It is very critical for the system to be able to allow the user to have more control on the execution. But for programmers, for Java programmers and C programmers, we know debuggers like a JDB or a GDB. So can we provide a debugger for the user to have in order to control the execution? That's why we enable the pause and resume and some of the advanced features like a breakpoints or conditional breakpoints. It's just some example features. And existing systems like Spark, Flink, um, open source solutions, none of them can deliver the features we want. So we decided to build a engine from scratch. The engine is called Amber. Uh, at a high level, it is a parallel data process engine. The reason we choose this feature is we want to deal with very large amount of data that has to rely on parallel computing. So in some of our use cases, we're dealing with the gigabytes of data. So when we reach that size, clearly we have to use parallel computing techniques. And the engine is based on the actor model. The actor model has been there for decades. Recently, it attracted more attention. One reason we chose this engine is the open source community has provided a few more mature solutions, like Microsoft's Orleans and the open source solution. Orleans is also open source. The other Java-based implementation called Akka, and these systems have been deployed in some other real systems, have been tested by other systems to show their reliability and independence and maturity. We choose to use this model. Plus, this model is very suitable for our data processing engine because conceptually, you can view each operator as one actor, and different operators talk to each other. That's very similar to the case where different actors talk to each other using message passing. So we benefit from what other people have done in the past few decades. And then we allow fast executions with the pause resume features. we allow debugging, and we allow the user to be able to, we allow user to modify the logic during the execution. That's especially useful when you do real-time debugging, and the whole system is fault tolerant. This is a very simple architecture. For some reason, it doesn't show the whole thing. Yeah, so it's a very simple architecture of the backend engine. I will not go through detail. So let me go through this one here. If the user submits a workflow, a very simple one shown on the top, our system will translate that workflow, which is a DAG, directed acyclic graph, into this DAG of actors. So you can see we can support parallelism. So this hash join in the logical level, it is a single logical operator, but physically it can become multiple physical operators or workers. The number of workers can be customized based on the need. If some operators are very expensive, you might want to allocate more workers. Some operators are much cheaper. You can just give one worker to that operator. So in this way, we can support this computation in parallel. And then the whole thing is sent to the backend actor model engine to run on cluster machines. So in one of our deployments, we were able to run the system on a cluster of 100 machines. Each machine has 4 cores. So that deployment was running the workflow on 400 cores. So it's massively parallel. And then the other thing is this figure shows how we really implement the pause and resume features. So at a high level, this is a DAG of the actors or workers, and then this is the structure of each operator. So the operator had this processing logic that really implements the key of computation, like selection join or some UDF operator, and the user provides code for this processing logic. Inside the engine, for this operator, we can have multiple input channels. Some of the channels are for receiving data. Some of the channels are receiving what we call control messages. The pause and resume, those requests are implemented as control messages and that are sent through a separate channel. That's why these messages, their delivery is not blocked by data messages, because data messages can be many and their processing can be slow. We want those control messages to be received and processed very quickly. That's why you saw in the previous demo, when Chris clicked the pause button, the execution can be paused almost immediately with a very low latency because of this internal design. There are more details about Amber, but I will skip the details. I'll just move on to the next topic. But before I talk about this cloud infrastructure, I wonder if there's any question from the audience. Okay. If no question, I'll continue. There are many challenges we're facing when we develop such a system. Here, I'm going to choose some of them to give some flavor of those very, very interesting research challenges and our solutions to those problems. The one main challenge we are facing in the last 1 or 2 years is really about scale. As we have more users, we want to build a cloud infrastructure that is scalable, reliable, safe for different users. So this is what we call the cloud infrastructure. Motivation, very simple. We want the system to be used by many people with different backgrounds, and we also want the system to be reliable when the number of users increases. And so how do we achieve the scalability for the system? This is our old single node architecture. It's a single stack with multiple layers, multiple components. We have some components for the user to upload or download either data sets or workflows. They can share, they can do version control. They can also do share editing. As you can see, two people all can work on the same workflow at the same time. We have a backend service for that purpose. And then on the engine side, we have, since it is a parallel system, it has a master node, it has multiple worker nodes, and then we have other features like, we didn't show it in the demo, when the user edits a UDF operator, that window really becomes a IDE editor. We have many advanced features like a coloring, highlighting, and auto completion, auto suggestion, and those features are really powered by a backend service. So in the old single node architecture, everything runs in a single computing unit. So this is not very reliable. In particular, challenge number one, the traffic can fluctuate over time. And when we did a summer program for high school students, they have a lot of workflows and executions during the class. And after class ended, then the server becomes very quiet. So how can you deal with this kind of a spiky workflow traffic workload to a website? So that's one challenge we will face. The second challenge is, let me see here. The solution to this issue is really about using microservice architecture. So we turn all the different components to different microservices and let each microservice manage their own lifecycle. So more to come in the next few slides. The second challenge is about how to allocate the resources for different users. Different different workflows, they require different kinds of computing resources. I mean, by computing resources, I mean CPU, memory, file system storage, and also GPU. For some workflows that need to do ML, either inference or training, you can imagine they might want to have a very powerful GPU to make the whole process more efficient. But for some other tasks, they may not need GPU, but they need half terabytes of memory. So and some other tasks could be very hungry for CPU cycles. So how can we allow different workflows with different resource requirements to run in a single platform? So clearly, the architecture of having a single node does not meet this requirement. So the way we do it is, as we have seen in the demo, before the user can run a workflow, the user has to request a computing unit, and you can specify the resources like amount of memory, number of cores, and down the road also GPU resources. And then once the user, excuse me, request such a compute unit, the infrastructure can allocate this compute unit dynamically, and then the user can just deploy or run that job into that unit. What's happening behind the scene is we run other pieces, components at different microservices. For this computing unit, we have a manager. When a user wants to start a computing unit, the computer unit manager will dynamically start a computer unit. Inside the unit, we can run the Ember runtime engine, as I explained earlier. Then the user, from now on, the user can just interact with the dynamically allocated computer unit to run the workflow. And then also when we do shared execution, which is not shown in the demo, two people or multiple people can monitor and observe the execution same workflow. And that feature is also implemented by letting this workflow run in this runtime engine. At the same time, a different user can come in, and the second user can also request another computing unit. That unit is dynamically allocated, and the user can run that workflow in that unit. And these different computing units don't share any memory or CPU cores. So we provide this kind of isolation at the computing layer. The third challenge is really about storage. If you pay attention to the details of this workflow, this is a very simple toy workflow. So we can see data comes in from here, and the data flows through the operators, and in the end, the results are saved. And you can see the different stages in this computation, they have different storage requirements. The source files read by one of the source operators, they tend to be in different formats, like CSV, images, ML models, or even video files. And so we treat all the data as just files, and we let each operator handle the format of the file. And then the output, since our back to your question, Jose, we choose the relational model to capture the semantic meaning of the intermediate results, also final results. The output has to find a home to be stored. So the output is treated as tables. And those intermediate edges, their intermediate results are also treated as tables. That's why there's no big difference between those intermediate results and final results. So clearly, the input, the output, they have different requirements regarding the semantics and the formats. So for this reason, what we decided to do is all the input files, we treat them as just files. And in the earlier demo, we showed this concept of a data set. A data set can be viewed as a collection of files organized as a tree structure, like a hierarchy of files. And then we also allow version control even on the data set, meaning if initially the user uploads one CSV file, and then they use it to do the analysis, and later the user decided to add either modify the file or add another file. So that's still treated as a part of the data set. So what we're doing for that case is we just increase the version by 1. So we create a new version of the data set. The user has the freedom to go back to any of the earlier versions to go to see that particular version of collection of files. So to enable all these features, we decided to use two open source solutions. One is called MinIO, the other one called LakeFS. You can view MinIO is an open source implementation of the Amazon's S3 storage format. It's very so if you use MinIO, you can natively migrate the whole thing to Amazon AWS or using their S3 format. And we also have this LakeFS layer that can manage the metadata of these files. And by using this combination of these two solutions, we support what we said earlier, which is a version-controlled collection of files, and also very efficiently. Because in some of the recent use cases, our collaborators are uploading like more than 10 gigabytes of files, and they also need to send a model, which is a trained ML model. The single model is about like a 10 to 11 gigabytes. So that's why it's very critical for a system to be able to handle this kind of very large amount of data. A very simple, interesting example is in one of the use cases, the user wants to upload like 8 gigabytes of files, and everything has to be done through the browser. And how to enable this kind of a fast upload experience? We tried a few other options, and it turns out that MinIO is very, very efficient for handling very large amount of data. This is for the input. For the output, since our model is relational, everything should be treated as tables. So we also, since we allow multiple workers to run at the same time, the solution has to support parallel writes. For sure, this is MinIO, they support parallel reads. For the output tables, they have to support parallel writes, and also also very nice ACID or transactional properties. So we chose to use the Apache Iceberg solution that meets our requirements. And then for those in addition to the input data, output data, we also have a lot of data about kind of a metadata like the users, access control, the data sets, all the runtime execution history. All the metadata has been stored in the relational database in Postgres. So this is our storage solution to meet the requirements of different stages. It's a kind of a very nice combination of multiple solutions to meet the demand. Okay, so this is the final infrastructure friendly for the cloud. We have a gateway running as a proxy, and behind the gateway we have different microservices. One microservice for community. Even this one could have multiple microservices, and then we have one microservice for share editing. We have microservice for runtime. Each of these computing units itself has its own resources, and this is the storage layer with the 3 different components. So everything together we use the Kubernetes software tool to manage the whole computing infrastructure. And we have gone through a few evolution phases of the architecture. In the first architecture, we used a single node diagram. And then about 2 years ago, when we did a summer program to teach high school students, we realized the single node solution doesn't work. We introduced another one with more redundancy. And now gradually we move into this architecture. And the very nice thing about this architecture is very cloud friendly. Most cloud service providers like AWS and GCP, they have a very nice support of Kubernetes, and then they also support auto scaling. And in this way, we don't need to worry about like running out of resources. This is our solution to the computing infrastructure challenge. So before I move on, I will pause here to see if there's any question from the audience. Okay. If no questions, Zhuoyu, how much time do I have left?
6 minutes, but you can go like as long as you want to.
Oh, I want to respect people's time. I will use the remaining 6 minutes. I'll talk about both of them. I may not go to details of like the AI component. In case people have questions, I have another student, Xiaojun, on the call. If you want to know more about how we use AI to improve the user experience. So I finish both topics in the remaining time. See, one focus we have right now is based on the feedback from our users. We want to see how we can make it easier for the user to use a platform to construct a workflow. Currently, each user has to come to a platform. They have to look at one of the operators and drag and drop the operator and connect the operators and to construct workflow. Of course, they can also share the workflow, but we want to make the process of constructing workflow much more efficient, much more user-friendly. So we are thinking about how to use the latest AI techniques to help the user in all different cases. So here I'm going to show you some of the features we are using. So one feature we are developing is how to develop this chatbot assistant. Right? So currently, we require the user to do drag and drop to construct workflow. What if we can do something similar to ChatGPT? Let the user talk to the system or type something to the system, and the system can just automatically recommend either operator or some Python code, and the user doesn't need to do everything from scratch. So this is one interface Xiaojun provided. You can see on this interface, we have this input box. The user can type in what they want. The system can just gradually construct this workflow. This is the user experience. Now, what's happening behind the scene is it's really a conversation between the user and the system. The user can just say what they want, and the system would just the backend would talk to an AI agent to understand what the user requests, and then generate, say, the next operator or a part of the Python code. And this is the architecture, so it might look very overwhelming, but at a high level, what's happening is our backend currently is relying on OpenAI's API. We can send the requests with some additional like information about the system, like the documentation or the description of the operators, and send this information to the OpenAI service, and then the service can give back to us what we want, and we show the results to the front end. Now, the details of this architecture, Xiaojun already have gone through a few architecture designs, and this is our current architecture design using multiple agents because the whole process is complicated. We want to rely on multiple agents to finish whole task, and each agent is responsible for one of the tasks. So this is a high level. If people have questions, we have time, we can talk about details, and Xiaojun is also on the call. So the second feature is when we talk to many collaborators, one of the common tasks they want to do is I already have some Python code or R code. Can I move the whole thing to your platform as a workflow? And previously, we do everything manually. This is very tedious, very time consuming. Some of the Python programs can take weeks or even months to finish. That's not efficient. So we are thinking about how we can rely on, again, latest large language models to automate the process as much as we can. So this is the one interface of the current ongoing effort. So on the right-hand side, the user provides a Jupyter notebook. And by using the backend, which talks to the OpenAI API, we can construct this workflow on the front end. And we can also build the mapping between this notebook cell and this operator. If the user click this one here, this one will be highlighted and vice versa. So in this way, we can reduce the amount of effort needed to migrate this Python code to workflow. The user still needs to do some validation to make sure the whole translation is correct. But at least they don't need to start from scratch. This is the backend architecture. I'll skip this one for now. The third one we are looking at is similar to the first one. During the process of constructing workflow, we want to be able to recommend some operators to the user, then based on the past history of other users. So here we are exploring the possibility of using another large language model to do the operator recommendation. So I use the remaining a few minutes to talk about the impact and our vision here. This table shows the statistics related to how this system has been used. At a high level, it's been used by many people in many workflows, produces many versions. Our whole team worked on different aspects of the project. It's very exciting to have such a system that has many research challenges that has been used by many users. To give a few examples, one space we're in is education. We have been using this system to teach more than five courses for people with different backgrounds. This is data science for all, data science for all for high school students. And this is a picture taken at the final project. The two high school students, they presented what they have done at the end of the program. This is a picture we took in one course called ISIS 80. We offered it in the last year at UCI. We taught 42 students from different departments like biology, math, art, and they use this system to learn data science, AI, ML. And this is another use case to test the usability and the reliability of the system. We have one very active project with the NIH. The vision of that project is to bring AI ML to the space of diabetes researchers. We all know the importance of the AI ML, and NIH wants to bring these kind of latest techniques to different communities. The community we're targeting is diabetes researchers, and the vision we have here is to use this system to build a platform. On a platform, they can just share the data sets, share the analysis as workflows, and eventually they also share the AI models. And since the whole platform provides a cloud infrastructure that allows people to do computation, not just the source code, then it can make AI ML sharing and reproducibility much easier. So this is a very active project we are working on with a few other colleagues. We are in the process of making the project Apache project. We have been accepted by the Apache incubator a few weeks ago, and it will take us about 1 year before we graduate, and then after that we can officially call us Apache Texera. Okay, I'll stop here. If people have questions, I will be very happy to answer those questions. The source code is on GitHub. The hub we showed earlier is also being tested. It's invitation only. If you're interested, you can either sign up or send them an email because we want to make sure the system is really fully functioning before we let more people use it.
I think this is great. I'll talk to you maybe one-on-one about AI capabilities and other things what's coming in the pipeline.
Okay.
Thank you.
Yeah, we have. I think Joy, you prepared a spreadsheet with all the available slots in the afternoon. I still have slots.
Yeah.
I'm available before 1.
Yeah, I just added my name to that.
Yeah.
So
Okay. Yeah. So we can do a one meeting in the afternoon.
yeah.
Okay, any more questions? Thank you so much for the talk and looking forward to the one-on-one in the afternoon.
Yeah, we have a few meetings in the afternoon. So thank you for coming to this presentation.
Thank you. Have a good weekend.
Okay, you too.